Good morning, everybody on the West Coast. Afternoon for everyone else. So again, welcome to our first complex webinar of the year. So what we're going to be doing is covering a little bit of a gentle introduction to parallel computing. So let me go ahead and share my slides. Okay, and maximize. Right, so and let me just re-emphasize one thing that Cindy Wong had said, and that is please fill out the surveys. They are very short, just a few questions. It gives us really important feedback. In fact, over the last year, we used the feedback that we received after our webinars to make some small adjustments to the to our plans for our agenda for this year. So, sorry, let me go ahead and minimize that. Okay, so we're going to be talking about parallel computing concepts, and my name is Bob Senkwitz. I'm presenting on behalf of the complex team here at the San Diego Supercomputer Center. Okay, so just a reminder, Complex is funded by the National Science Foundation. It is a cyber training award to cover non-programming skills needed to effectively use supercomputers. So the topics for this year are going to include parallel computing concepts, Linux tools and bash scripting, cybersecurity, batch computing, how to get help, data management, and interactive computing. So a quick overview of what we're going to be covering over the next hour. So we're going to be beginning with an introduction. We're then going to get into processes, threads, MPI, and OpenMP, talk a little bit about hybrid applications, Amdahl's law, other limits on the scalability of parallel applications, running parallel applications, and performing scaling studies, and then finally wrapping up with where to go next and some conclusions. So I'm going to guess that the reason most of you are here is that your workloads, your computational work, has grown to the point where you can no longer run everything you need to do on your local resources. For example, a laptop, a desktop system. Specifically, you may need to start using parallel computing. So this session is intended for anyone who currently runs, plans to run, or is even thinking about running applications on parallel computers. If you are writing proposals for computer time on campus clusters, nationally allocated systems, or other resources, I know that we may have a few more senior folks in the webinar today who maybe are not so much involved in hands-on programming, but still you might be in charge of writing that proposal in order to get computer time. So I think you'll find this presentation very helpful, especially when we get into the scaling studies near the end of the talk. If you're purchasing time and compute resources and you want to maximize your return on investment, if you're considering purchasing hardware for your lab, or if you're just curious about parallel computing. So the motivation for this talk, and in fact the entire complex series, is that much of the training in parallel computing is targeted at people who write their own parallel applications, and it focuses on programmer topics. MPI, OpenMP, CUDA, profiling, performance tuning. These are all very, very important topics, but if you are not a programmer, if you're not actually a developer, you may not necessarily need these topics. And as a consequence, since there's so much emphasis on actual programming, I'm going to say that many end users who are not developers rarely or never get a proper introduction to parallel computing. So even if you don't write code, it's still going to be important that you understand some of the basic principles of parallel computing so that you can make the most effective use of valuable advanced cyber infrastructure. So I'm going to quickly cover a few myths about parallel computing. First is that parallel computing is for astrophysicists, engineers, climate modelers, and others working in traditionally math-intensive fields. And I hope that if you come from what we often call non-traditional fields, things that are a little less math intensive, that you already realize this is a myth. So years ago, when I started at Supercomputer Center in the late 90s, this might have been partially true. But today, pretty much every field of research makes use of parallel computing. And this does include the social sciences, life sciences, arts and humanities, in addition to physics, chemistry, engineering, material science, and what we call the other usual suspects. So another myth of parallel computing is that throwing more hardware at a problem will automatically reduce the time to solution. This is something that comes up often in social situations where I explain to somebody I work at a supercomputer center, and they're like, "Oh, you would be able to take a problem and just solve it in 5 seconds," or you might be able to do a whole lifetime of research in an afternoon. And I always have to remind them that parallel computing is a little more complicated than that. It's only going to help if you have an application that has been written to take advantage of parallel hardware. And even if you do have parallel code, there's going to be an inherent limit on the scalability. So one caveat is that if you have a high throughput computing workload, you can use parallel computing to run many single core or single GPU instances of an application and achieve near perfect scaling. And then the third myth is finally that you need to be a programmer or a software developer in order to make use of parallel computing. And in fact, most users of parallel computers nowadays are not programmers. Instead, they use mature third-party software that had been developed elsewhere and made available to the community. So to summarize, many of you are going to be using somebody else's code. So if you're doing climate and weather modeling, you might be using WRF. If you're doing molecular dynamics simulations, biological systems, you might use AMBER or NAMD or other programs. If you're constructing phylogenetic trees, you might use RaxML, Mr. Bayes and others. And if you're doing electronic structure calculation, maybe CP2K. So very, very briefly, modern clusters and parallel computers, they consist of multiple compute nodes connected by a fast network. And each CPU node typically contains one or more, typically 2 multi-core processors, while GPU nodes typically contain 4 GPUs. So to effectively use this hardware, we need applications that have been parallelized so that they can run across multiple cores or multiple GPUs within a node or across multiple nodes. So now we're going to start getting into processes, threads, and OpenMP. So processes and threads are both independent sequences of execution. You could think of a process as being an instance of a program with access to its own memory, state, and file descriptors. So processes can open and close files. Threads are lighter weight entities that execute inside a process. So every process is going to have at least one thread. You get one thread by default. And threads within a process can access shared memory. So sometimes you'll hear threaded parallel computing referred to as shared memory programming. So online resources describing the differences between threads and processes, they often tend to be geared toward computer scientists, but I found a couple of resources that I think do a reasonable job of addressing the topic, and I should have listed these in the opposite order. The second one is a little bit more of an informal approach to processes and threads, if you'd like to go a little bit deeper. And if you want to go deeper still, you can look at this thread on Stack Overflow, where it gets more into the distinction between processes and threads with a computer science sort of a spin. So processes, they incur more overhead, but they're also more flexible. Multiple processes can be run within a compute node, or they can be run across multiple compute nodes, what we call distributed memory computing. Threads, they incur less overhead. Threaded codes can also use less memory since threads within a process have access to the same shared data structures. Now, the one downside of threads, though, is that they're less flexible, multiple threads associated with the process can only be run within a compute node, so they need access to that shared memory. So processes and threads, why do I care? Especially if you're not a developer. So the type of parallelization is going to determine how and where you can run your code. So distributed memory applications, multiple processes or multiple instances of a program, they can be run on one or more nodes. So if you have highly scalable applications that say can use a significant portion of a supercomputer, it's going to be a distributed memory application. Shared memory applications should only be run on a single node. You're not going to get any benefit going across multiple nodes. In fact, you're just going to waste resources. Hybrid applications can be run on one or more nodes, but you need to consider the balance between threads and processes, and we're going to be discussing hybrid applications shortly. And in all cases, you may need to consider how processes and threads are mapped and bound to cores. In addition, being aware of threads and processes are going to help you to understand how your code is utilizing the hardware and how you can identify some common problems. So we're going to talk briefly about MPI, the message passing interface, and OpenMP. So these are programmer topics, but you still need to be aware of what these are. So MPI is a standard for parallelizing C, C++, and Fortran codes so that they can run on distributed memory, multiple compute node systems. So although they're not officially adopted by any major standards body, it's become the de facto standard, i.e. almost everyone uses it. There are multiple open source implementations, and this is where things get a little confusing. You might hear about MPI, and then in the discussion might cover things like OpenMPI, MVAPIC, and MPIC. These are just different implementations of MPI. Now, MPI applications can be run within a single shared memory node. All widely used MPI implementations are optimized to take advantage of the faster intranode communications. MPI is portable, it can be used anywhere. And although MPI is often synonymous with distributed memory parallelization, other options are gaining adoption, such as Charm++, UPC, and X10. But mostly, your distributed memory applications are going to be written using MPI. So although we're discussing MPI, the same principles apply when parallelizing deep learning applications. For example, Horovod is a distributed deep learning training framework for TensorFlow, Keras, PyTorch, and Apache MXNet. And Nickel, the NVIDIA Collective Communication Library, implements multi-GPU and multi-node communication primitives optimized for NVIDIA GPUs. So to show you an example of an MPI code, again, keep in mind if you are not a programmer or an application developer, you do not need to know MPI. You just need to be aware that it exists, and that if you're building your own executables, you'll need to use the appropriate wrappers during the build process. So MPI applications are pretty dense. They're written at a low level. Data is explicitly communicated between processes using calls to MPI library routines. So again, if you're not a programmer, you could kind of step back, not worry too much about the details of the example. If you have a little bit of programming experience though, I'm going to show here how you would parallelize a C or C++ program of Hello World. So you can see when we create a parallel version using MPI, we had to add quite a bit of code. I have that highlighted here in purple and bold. So we needed to include a header, mpi.h, so that we have access to the MPI library prototypes. We need to initialize the environment, that is the MPI init call. We need to get the number of processes. We need to get the rank of each process, so each process is going to be numbered. We want to get the name of the processor that each process is running on. And then we're going to have hello world print from each processor, listing its rank and the number of processes and the processor name. And then finally, we will finalize the MPI environment. So this is a little bit of an extreme example because the amount of MPI code relative to the initial code is much larger than you would have in a real life application. But it does show that it's a little more complicated, and we haven't even gotten into communications between the processes. Main thing I want you to take away from this is that it's a way of adding functionality to your code, and it operates at a very low level. Now, OpenMP is an application programming interface for shared memory parallel programming in C, C++, and Fortran. It's a little bit easier to use. It mostly works around compiler directives, plus there are a few library routines and environment variables. OpenMP, unlike MPI, is supported directly by the compiler. And as far as I know, it is supported by all major compilers, including IBM, Intel, GCC, PGI, and AMD's optimizing C and C++ compilers. OpenMP is portable, and like MPI, could be used anywhere. And although OpenMP is often synonymous with shared memory parallelization, there are other options: Silk, POSIX threads or pthreads, specialized libraries for Python, R, and other programming languages. So like we did for MPI, we're going to look at a brief example of how a OpenMP code would be parallelized. So again, if you're a programmer, you do not need to know OpenMP, but you just need to be aware that it exists. And if you were building your executable, if you've downloaded code and you actually need to compile the binary, you need to be aware that this is an OpenMP code and use the appropriate compiler flags. So hopefully, if you're downloading somebody else's code, they will have make files and the scripts that you need in order to do this. But on occasion, you may need to go in there, change some of the flags, depending on which compiler you're using. So in this example, we have a very short snippet of C code where we're initializing a few arrays A and B, and then we're adding them element by element and storing them in array C. So it's in this last loop where the real work is being done. And what we want to do is parallelize that loop. So again, working in a shared memory environment, where in addition to including omp.h, defining a few variables, the real crux of the parallelization is in that pragma OMP parallel for example. So what we're doing here is taking the iterations of that loop and we're going to distribute them across the threads. So the big picture, looking at MPI and OpenMP, MPI is used for managing multiple processes, and it's implemented in libraries such as mpich, mvapich, OpenMP, and vendor-specific implementations. OpenMP is used for managing multiple threads, and OpenMP is implemented by the compilers, GCC, PGI, Intel, and others. Okay, so we're going to switch gears. We're going to be looking at hybrid applications. So many modern parallel applications are built using a hybrid approach to take advantage of both distributed and shared memory. This is typically going to involve MPI and OpenMP, although other combinations are possible. So hybrid codes have some advantages over purely shared or distributed memory applications. So a shared memory application can have limited scalability within a node, and it cannot be run across multiple nodes. Distributed memory apps, although they are more flexible, they allow us to run across multiple compute nodes, they have higher memory requirements and more overhead when running within a node. So back in the early days of multi-core processors, the hybrid approach really didn't have too much of an advantage. We found that a straight MPI application was often more efficient than a hybrid application. But as the number of cores on nodes has grown, so typically CPU nodes now will have 128 or more, cores, we find that we often get better performance if we use a mix of the two approaches. So we're going to look at a simplified parallel computer. Consists of just 2 nodes, each with 16 cores, and they are joined by a network. So this large gray box on either side of the network is a compute node, and each of those blue boxes represents a core, a CPU core. So if we have a pure message passing application, say developed using MPI, we're typically going to execute 1 process per core. So this is a case where we see 32 processes run across 2 16-core nodes, with each process running on 1 core. Now you can have multiple processes running on a core, but it's not going to buy you anything. What's going to end up happening is that those multiple processes are going to be competing with each other. So if we have 2 processes running on a core, each of them is going to get 50% of the time, so we're not going to get any potential speed up. So typically, we're going to use 1 process per core. Now, if we have a threaded application, say parallelized using only OpenMP, we're going to be restricted to running within a single node. So in this case, we see a threaded application, single process running 16 threads across 16 cores. So again, we have 1 process represented by that large orange box, and there's going to be 1 thread per core. Now, technically, any programming model can be mapped to any hardware, but in practice, threaded applications are run within a single node for the best performance. So about a dozen years ago, we had a supercomputer here in San Diego called Gordon, where one of our innovative features was we implemented something called VSMP. It was a software layer that would aggregate the memory and the cores from multiple nodes to make it look like a large shared memory machine. So although we could program it like that, we found that the overhead of moving data across the network was just prohibitive, and there was really no real use cases where we would benefit from doing that. So again, shared memory applications, think of running just within a single node. Now, hybrid applications are where things get a little more interesting. Again, typically MPI plus OpenMP. Any combination of threads and processes within a node is allowed. So this example shows 2 processes per node and 8 threads per process. So we can see in each node that we have 2 orange boxes spanning 8 cores, and then we're going to have 8 threads within each of those processes. So a typical scenario is to run 1 process per node and use threads within the node. But as I mentioned earlier, this is becoming a little less common as the number of cores on a node continues to grow. Now for hybrid applications, it gets a little challenging trying to decide the balance between processes and threads, given the range of options from 1 process per node to 1 process per core. So in order to choose, we're going to need to consider the performance, the runtime, and the memory usage. And we're going to talk about that a little bit later when we look into scaling studies. So if you do have a hybrid application, you might need to run different combinations of processes and cores to figure out which gives you the best performance. All right, so we're now going to move into Amdahl's law. So Amdahl's law describes the absolute limit on the speed up of a code as a function of the proportion of the code that can be parallelized and the number of processors. So this is the most fundamental law of parallel computing. If you only know one, let's say, law of parallel computing, this is the one to know. So it's a little theoretical. We're going to start off with P being the fraction in the code that could be parallelized. So again, a little abstract. You can't really look at the code, and unless it's a very, very simple code, you won't be able to kind of eyeball it and say, okay, 50% or 75% of this code could be parallelized. S is the fraction of the code that must be run sequentially. So it's 1 minus P. So basically anything that cannot be parallelized is going to be run sequentially. And N is the number of processors. Again, we're not really concerned with whether our parallelization is done using shared memory parallelization, say with OpenMP, or distributed memory with MPI. Just think number of processes. So the speed up that we're going to get is going to be 1 divided by 1 minus p, which is the serial content, plus p over n. So what this is telling us is, if you look at that last term there, p over n, if we have code that could be parallelized, in theory, if we take that parallel content, we should be able to spread that across any number of processors and get a proportional reduction in the runtime. And if we go in the limit, where we have an infinite number of processors, the theoretical upper speedup that we're going to get is going to depend only on the proportion of the serial content. So as n goes to infinity, p over n is going to go to 0. We're left with 1 over 1 minus p, which equals 1 over s. So that doesn't look too bad, but as we're going to show in the next slide, it doesn't take much serial content in order to impact the speedup. So this is the plot that I generated showing the speedup of code with 50%, 75%, 90%, and 95% parallel content. The max speedup that we could get for those 4 cases is 2, 4, 10, and 20. So even if we had only 5% serial content or 95% parallel content, the maximum speedup that we're going to be able to get is only a factor of 20. Now, if we go a little bit further, let's look at a code that has 99% parallel content. Even that would make terrible use of a modern 128 core node. So if we take p equal to 99%, the maximum speedup that we're going to get is going to be 100. So no matter how many processes, how many compute cores we use, we're never going to be able to run this more than 100 times faster than on a single processor. And even more, keep in mind that that max speedup is an absolute limit. If we look at the scaling curve, if we look at speedup as the number of cores, and I have an arrow here pointing to the spot where we'd have 128 cores, even with 99% parallel content, we're only getting a 60% speed up on a modern 128 core node, and which is unacceptably low. We would never want you to run with such a poor parallel efficiency. Okay, in addition to Amdahl's law, there are other limits on scalability. So Amdahl's law sets a theoretical upper limit on the speedup, but there are other factors that affect scalability. So first, we're going to be limited by the problem size. Next, we're going to have limits based on the communications overhead. And finally, uneven load balancing is going to affect our speedup. So in real-life applications that involve communication, synchronization, say points where all the threads of processes must complete their work before proceeding, or if we have irregular problems, say computational fluid dynamics or magnetohydrodynamics, over complex non-Cartesian grids, the speedup can be much less than predicted by Amdahl's law. So I'm going to start with problem size limitations. And I want to point out here that the reason I'm using Hello Kitty with the paintbrush is that it was the only public domain image with a transparent background of a character with the paintbrush that I could find. But that aside, let's look at the case where we have one kitty has the task of painting a fence. And let's say that it takes 48 minutes. So we'd imagine if we had 2, that they would be able to paint the same fence in 24 minutes. So we assume that they both work at the same rate. We give them an equal portion of the fence paint. 2 of them should be able to do the work in about half the time. Now, if we have 4 Hello Kitties, we might expect them to take 12 minutes to paint the fence. Now we get up to 8. Might take 6 minutes to paint the fence, but we could see that it's going to be a little doubtful. It's getting crowded. Essentially, we don't have enough work to go around. And if we go to an extreme example where there's 32 Hello Kitty trying to paint this section of fence, there's definitely not enough work. So not only will we get to the point where there's not enough work to keep all your processors or GPUs busy, but you may actually see your application run slower since the parallel overhead overwhelms the runtime. Another factor is uneven load balancing. So parallelizing the code requires dividing the computational work into chunks that can be executed independently. So if the work cannot be distributed evenly, then processors are going to sit idle, waiting for the longest chunk to finish. So let's look at this case where we have 4 units of work that need to be done. They all take a little bit different time, and that the first 4 need to be completed before the second 4 are started. So what we're going to do is take these chunks of work, we're going to assign them to CPUs 0, 1, 2, and 3. And we're going to see that the work that was assigned to CPU 2 is a little bit larger than what was given to 0, 1, or 3. So what's going to happen is that CPU 1, which has the smallest amount of work, is going to finish first, and it's going to be sitting there idle until the other process is finished. Then CPU 3 is going to finish, it's going to sit idle, CPU 0. All 3 of these are going to be waiting for CPU 2 to finish its work. Then we hit a synchronization point, and now we assign our next batch's work, and this time CPU 1 got the largest chunk. So CPU 1 is still going to be working while 0, 2, and 3 are idle. So this is going to impact the speed up that you're going to get. And then finally, really common example is communications overhead. And this is going to come up a lot in solutions of partial differential equations, say computational fluid dynamics, magnetohydrodynamics, dynamics, climate, weather, and many other simulations involving systems of partial differential equations solved on a grid that is distributed across processors. So let's take our 16 by 16 grid, and we're going to divide it into 4 8 by 8 chunks that are distributed across 4 different processes, 0, 1, 2, and 3. And we're going to assume that each cell is updated using the values of the 4 neighboring cells. This is a very common approach to solving partial differential equations based on finite differences. So you could see that for most of the cells, they can work independently. So I show in each case a red cell and then the 4 neighboring cells in dark blue. So for those cells that are in the interior of each chunk, the calculations can be done within each process. But for cells that are at the boundaries, data belonging to the neighboring process is needed. And in order to accommodate this, we need a halo of ghost cells, and data must be communicated between the processes. And the data movement is going to depend on both the latency and the bandwidth of the network, and this is going to introduce some communications overhead. So we're going to see that we're going to communicate columns or rows of cells between the processes. And then after we perform that communications, then we can complete the calculations on those cells that are in the boundary of each chunk. So at this point, you might be thinking, how does anybody do parallel computing? How do they do it efficiently? And I'm going to say all is not lost. You've got these hard limits imposed by Amdahl's law. We've got these other factors that we just looked at. So how does anybody ever use all of the cores on a single modern compute node, let alone the full power of a large supercomputer? So first of all, the reality is that most parallel applications do not scale to thousands or even hundreds of cores. And the applications that do achieve high scalability, they employ several strategies. First is that they don't look at a fixed size problem, but as they run on more and more hardware, they'll grow the problem size with the number of cores or nodes. They're going to overlap communications with computation. They could use dynamic load balancing to assign work to cores as they become idle. And you can also increase the ratio of the computation to communications. So problem size limitations solve a larger problem. We don't stick with the smallest problem and try to run that on more and more cores. Instead, what we'll do is take advantage of our parallel computers to run larger problems that we couldn't have run on a single node. So in this case, going back to the 32 Hello Kitty, they can easily paint a much larger fence in 1/32nd of the time. Communications overhead. We can overlap computation with communication. So on the left, we highlighted the cells that are at the interior of each domain. So, and we highlighted these in red. So we can do the calculations on those cells while the communications is going on in the background. And then once the communications finishes, we can finish the computations around the edges of those domains. We could use dynamic load balancing. So let's say we have a set of tasks that could all be performed independently, but they take varying amounts of time. So if we did a static assignment of tasks to processes, this can lead to a large load imbalance, depending on the ordering of these tasks. So we can get better performance if we dynamically assign work to processes as they become idle. So let's say that I had 8 tasks to complete, label them A through H, and we just take the first 4 and we assign it to processor 0 and the next 4 to processor 1. So just by bad luck, processor 0 got 2 very, very time-consuming tasks, A and B, and then 2 smaller tasks, C and D, whereas processor 1 was assigned these 4 much smaller, much quicker tasks. So if we just assigned statically those first 4 to processor 0, the next 4 to processor 1, processor 1 is going to finish its work early, and it's going to have to wait a long time for processor 0 to finish. Instead, and again, we're assuming that all of these tasks are independent, if we assign them dynamically, say give task A to processor 0, task B to processor 1, and then as these processes become idle, giving them the next chunk of work, we could achieve a much better load balancing. It's never going to be quite perfect, but in this case, we were able to significantly reduce the time to solution. Okay, so finally, we're going to get into some very practical matters. And this is running parallel applications and carrying out scaling studies. So we've covered the basic concept of parallel computing. We looked at hardware, threads, processes, hybrid applications, the implementations of parallelization, say using MPI and OpenMP, Amdahl's law, and other factors that affect scalability. So all of this theory and background, it's great, it's very useful, but we still left the question of how do we determine how many CPUs and GPUs to use when running our parallel application? And the only way to definitively answer this question is to perform a scaling study using a representative problem run on different numbers of processors. So earlier when we talked about Amdahl's law, again, it was very, very theoretical. We talked about the parallel content and the serial content of the code. If you have a very, very simple application, say if we go back to my OpenMP example where we initialize a couple arrays and then we parallelize the loop where we're adding 2 of the arrays, we could kind of eyeball that and figure out how much of the code is parallel. In that case, it was nearly all. But in real applications, we're not going to be able to look at the code and tell how much parallel content we have. So when we run this representative problem, and by representative, I mean one with the same grid size, the grid dimensions, the number of particles, number of images, number of genomes, the same complexity, say the level of theory, the type of analysis, the physics that's included as the research problem you want to solve. Now, this doesn't mean that you need to run the entire problem. Let's say we're doing a global climate simulation. There will be many, many, many time steps. We don't need to run it out for 10 years or 100 years or 1,000 years, however long our calculation is going to be. We could do just a few time steps. If we're doing molecular dynamics, again, we don't need to run out to microseconds. We could just look at a few picoseconds of time. Okay, so when we do our scaling studies, essentially we're going to run our application on different numbers of cores, and we're going to record the time and try to determine how many cores we should be running on. Now, this is an example of presenting scaling results the wrong way. We see this very often in applications for computer time, where we have the runtime as a function of the number of cores shown on linear axes. Now, believe it or not, these two codes have very, very different behavior. But if we look at these graphs, it's really hard to tell which one is better. At large core counts, it's pretty indistinguishable. So what we're going to do instead is when we present scaling results, what I call the right way, is we're going to use log axes. Now, in this case, if we use logarithmic axes, we should see we should see a straight line if we have perfect linear scalability. And I've gone one step further. On the left axis, I'm showing the runtime as a function of number of cores. On the right axis, I'm showing the parallel efficiency as the number of cores. Parallel efficiency is just the speed up divided by the number of cores. So if you ran on 100 cores, the code ran in 1/100th of the time, that would be perfect parallel efficiency. And the other thing I've done is I've added a line, a solid black line, showing linear scalability. So again, keep in mind that this is the same data that we saw in the previous slide. Now it looks completely different. On the left-hand side, we're seeing an example of strong scaling where we have perfect scalability. On the figure on the right, we see that we get linear speed up out to about 10 cores or so. But then after that, it really trails off, and then we see a drop in the parallel efficiency. And I see that there is a chat message, so I'm going to go ahead and answer that. Okay, yeah, we'll cover that later. Okay, so where should I be on the scaling curve? If your work is not particularly sensitive to the time to complete a single run, consider using a CPU or a GPU count at or very close to 100% efficiency. Sometimes this might mean running on a single core. And this especially makes sense if you're doing parameter sweep workloads, where the same calculation is run many times with different sets of input. So in this case, you probably don't care about the result of any single calculation, but what you do need is the entire ensemble of results. So I would say run out here, looking at our realistic example, out here at relatively small core counts, where your efficiency is staying over 80%. Now, sometimes you're going to have to go a little bit further out on the scaling curve if the job would take an unreasonably long time at lower core counts, or if a shorter time to solution helps you make progress in your research. Now, if your code does not have checkpoint restart capabilities, this is really common, say, in phylogenetic codes where we're constructing trees of life, and the runtime would exceed the queue limits, you'll have no choice but to run at higher core counts. So in that case, you might go a little bit further out, consider slightly lower parallel efficiencies. Now, sometimes if time to solution is really critical, it's okay to run at lower efficiencies. So the examples might include calculations that need to run on a regular schedule. Say this is part of a laboratory workflow where data is collected each day and it has to be processed overnight, or if you're doing severe weather forecasting. Now, I know you're not going to be using our systems for hurricane tracking or tornado prediction. But if you were in that sort of an environment, I would say, run on all the hardware that you have available, as long as you don't get to the point where time to solution actually increases. So what I show here is, for example, minimum core counts needed to process data overnight. And then out here, say something really important like a tornado or tsunami prediction. And one other consideration is if you have large memory requirements, sometimes you might need to request, you might want to use extra cores so that you get enough memory for your application. And then so I'm going to wrap up here. We're just a little bit before the hour. Where to go next and conclusions. So I'm going to say we really only scratched the surface. This was a very, very quick introduction to parallel computing. We're assuming that you're all kind of new to parallel computing and just want to get a little taste of what's involved. So we have many training resources covering a wide range of topics. For the nationally allocated resources, you're going to find, through Access, they have links to the user guide and lists of systems. So in conclusion, and this is my last slide, and then I'm going to answer a few questions. Parallel computing is for everyone who wants to accomplish more research and solve more challenging problems. You don't need to be a programmer, but you do need to know some of the fundamentals to effectively use parallel computers. Processes are instances of programs. Threads run within a process and access shared data. MPI and OpenMP are used parallelized codes. Amdahl's law imposes an upper limit on scalability, but there are other factors that impact scalability: load imbalance, communications overhead, and so on. And probably the most important takeaway from this talk, especially if you are involved in writing the proposals for computer time, is that it's important that you properly display your scaling data and use that to justify your core counts. And finally, the code that I use to generate some of the figures in this presentation are available through our GitHub repo. In fact, I'm going to stop sharing here. I'm going to go to the GitHub repo. So if you go to the repo, you will see that there are two notebooks in there. Well, one that I used to generate the figures for Amdahl's law, and another showing strong scaling. And you could either run these using Binder, or I would suggest just downloading, installing Anaconda locally, which is what I did here, and you can work through the examples. So I show here how I generated the plots, illustrating Amdahl's law for both 50% through 95% and 50% through 99% parallel content. So I'm going to suggest, if you're curious, go in there and play around a little bit. Maybe even look at 99.9 and 0.99% parallel content. Go to the right tab here. And for strong scaling, I have the code here that I use to generate plots for strong scaling on linear axes and on log axes. And in fact, you could go here, just plug your own data in, and you can generate scaling plots that you can cut and paste into your allocation proposal. And with that, I am going to stop, and I'm happy to take any questions.